Dear students, in this video we start topic 3b, or in new version topic 4, about vapor liquid equilibrium. So far we have learned about the vapor liquid equilibrium for different systems such as polar mixture, non-polar mixture. But if we have very high deviation from ideality for liquid systems, in this case we have limited miscibility for liquid systems, and in this case we have liquid equilibrium and vapor liquid equilibrium. We have two different phases, immiscible phases, such as oil and water. The first section of topic 4 or 3b is related to PVT diagrams. In slide number 14, section 4.3, of course you know this PT diagram, PV diagram. Okay, in this section, we add composition to our diagrams. For pressure, volume, temperature diagrams, we select only two-dimensional diagrams. For example, pressure, volume, pressure, temperature, or temperature, volume. Of course, if we have mixture, we should add composition to these diagrams. For example, in this PT diagram, we add XY axis or composition axis to our diagram. Again, we get three-dimensional diagram, and again, in order to start easier, we select only two-dimensional. But here you can see, here we have envelope type diagram. You can see P2C2 line, saturated line for component number 2. C2 is critical point of component 2, and P1C1 is saturated line of component 1. Here we have upper surface. Upper surface, it means that P2C2, P1C1 upper surface is related to saturated liquid or bubble point surface, and lower surface is related to saturated vapor, and we call it dew point surface. Between these two surfaces or plates, we have two-phase region. Okay, again we select only two-dimensional, for example PT, TXY, or PXY. Firstly, we are going to learn PT diagrams. If we have binary systems, we get this type graph. Of course, XC1 and SC2 are related to pure species 1 and 2 respectively. Here we have WCPCMCTV curve related to our mixture. Here WCPCM is saturated liquid line or bubble point lines, WCPCM, and CMCTV, this curve is related to saturated vapor or dew point of mixture. Of course, what the CP is critical pressure or highest pressure of our mixture. We called it critical condensation pressure or Cree-Condon bar. And CT is highest temperature of our mixture or critical temperature of mixture or Cree-Condon therm. CM is critical of mixture. Okay. And of course here we have these lines, gray lines, related to or standard line. We call it standard line, related to different composition. For example, on the WCPCM line we have 100% liquid. On this first gray line we have 75%. The second is 50%, and decreasing up to WCTCM line where we have 0% liquid. Okay. It's about the PT diagram for binary system. We can see here dew point and bubble point, and in this slide you can see increasing temperature from this point to this point at constant pressure. Of course, here what happened, firstly we have liquid phase, increasing temperature caused to intercept this bubble point curve. We have saturated liquid, we call it temperature or bubble point or mixture, and here we have two-phase region. Increasing temperature caused to intersect the CMCTW line, CMCTV line, sorry, this line, where we called it temperature of dew point, and after this point we have vapor. Okay, consider a subcooled liquid undergoing an isothermal decreasing of pressure. Point A, here we have subcooled liquid. At constant temperature we decrease pressure. At point B we have saturated liquid or bubble point. Further decreasing we have two-phase region. At point D we have saturated vapor or dew point, and point E we have fully vapor phase. But if we shift point A to any point after Cm, right side of Cm, it means that we have a supercritical region, and we are going to decrease pressure at this point. What happened? Isothermally we are going to decrease pressure from this point. What happened to our systems? Let's go to other slides. In this slide you can see here we have bubble point line up to Cm point and dew point line with 0% liquid. Here we have 100% liquid, 75%, 50%, 25%, 10%, 5%. We call them standard lines. Okay, if we decrease pressure from point 1, of course, firstly this line intercept dew point line. We can see dew point line or dotted line, dew point line, where we have 0% liquid. Further decreasing of pressure causes to increasing of liquid ratio or liquid phase. You can see here we have 5% liquid. From this point to this point, we have increasing of liquid in our systems from 0 to 5%. And if we decrease pressure, we have increasing of liquid phase. It's a reverse condensation. It's one of the famous phenomena in thermodynamics. We call it retrograde condensation. By decreasing pressure, we have increasing in liquid ratio, liquid phase in our systems. So after this point, it means that bubble point, again we have decreasing in liquid phase, and so we have point 2, and finally again intercept dew point, 0% liquid, and point 3 fully vapor. We call this phenomena as retrograde condensation. Retrograde condensation. So remember this slide, it's very important. Petroleum engineers know this retrograde condensation because it's very useful to reservoir engineering, and I think that chemical engineers, it's the first time to learn this one, retrograde condensation. Okay. Please review these sections. In the next video, I'll try to finish the first section and start the second part, or partial miscible liquids. Okay, good luck.